Hey, let's do more calculus together. In this lecture, we're going to be in section 5.2 in our textbook, which is about the definite integral. This section builds on the previous content, which was about approximating areas under curves. And in this section, we're going to use the definite integral to define exact areas. Okay, so this section is all about defining exact areas. It doesn't say how to compute them necessarily, except in terms of integration by geometry, which is one of our main goals. So we're going to compute some integrals using geometry. And we're going to start building familiarity with the rules for how to manipulate integrals. And we're also going to talk about the definition of the integral. So as far as how do you actually compute these things in general, that's coming. We're not quite there. So we're stepping up to that. I would like to point out that consistent with the stuff in chapter 5, I have quite a few videos on these topics. And so I'd like to highlight this one right here, this integration by geometry, and this properties of the definite integral as being two particularly relevant videos. And those of you who are going on to Calc 2 may enjoy the integral of sine of x as a Riemann sum, where I formulate that explicitly. Maybe other people would be interested in it too, but I do know that people who are going to go into Calc 2 are going to have to work with series and sums, and so that's why I think you might want to take a look at that one, just to keep building that familiarity with summation notation. So the first thing I want to do with you in this video is to define the definite integral. And I'm not going to do that at this particular moment, but I'm going to draw some rectangles. And I wanted to do this to talk about two things. There are two things that I want to try to convey in this section right here. I want to convey what a partition is and what sample points are, because in order to define a generic Riemann sum, in order to define the integral, we have to talk about those two things. So what I'm going to do is I'm going to start by drawing a curve, and it doesn't really matter what the curve looks like here. I'll put a corner in it. It doesn't really matter. We could put jumps in it if we wanted. Jumps are okay in this case, so it doesn't have to be continuous. We're going to focus our attention, as usual, on some interval from A to B. What I'd like to do is I'd like to divide this up into a bunch of subintervals, and I'm going to do this in this case. I'm going to put in those subintervals non-uniformly. Okay, so what I drew was these things, and they're not uniformly spaced, and that was deliberate. That's because the definition for the integral does not require a uniform partition. That's just something that makes it computationally feasible by hand. Okay, so I have some intervals here. I have interval 1, the next one interval 2, blah, 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 until I have my interval n. And I've got my my points that separate those things. My focus isn't necessarily on those values, but I do want to label them x0, x1, x2, x3, all the way down until I get to x sub n is my last one, x sub n minus 1, and that one right there is x sub n minus 2. Okay. So what I'd like to do is I would like to note that each of these intervals here has a distinct width, a possibly distinct width, right? I should probably do that in purple so it stands out more than the lilac. So the width of the ith interval is what we're going to write as x sub I minus x sub I minus 1. Right? So all I'm doing is taking x sub I and x sub I minus 1, and I'm calculating the distance between those. We've been doing distances between points a lot this semester, and that's relevant right now. So the partition is the set of intervals. And the width of the partition is the max width of any subinterval. So in what we've drawn here, I have a bunch of subintervals, and the widest one is the one that defines the width of the partition. So that one right there is the widest interval, subinterval. And so the width of that determines the width of the partition. Okay. The reason that we're going through this will become clear as we do the definition. So what we're going to do is we're going to take the limit as the width of the partition goes to 0. So I need to draw a few more things in here because I said I wanted to do both partition and sample points. So let's zoom in a bit further here, and I'm going to put a blue circle somewhere in each of these intervals. And it doesn't have to be in the center. It doesn't have to be all on the left. It doesn't have to be all on the right. I've got these sample points. Ooh, I'll put a little yellow in it to really make it pop. All right. So these blue points with the yellow dot in the center, those are my sample points. Blue dot with yellow in the middle, that's a sample point. We're going to call those C sub I. This is C sub 1, C sub 2, C sub 3, C sub n, C sub n minus 1, C sub n minus 2. So our setup essentially is that I have a partition. Okay, that's a bunch of subintervals. And each subinterval has a marked point. It doesn't matter how it was determined. All it matters is that it was a marked point inside that subinterval at which we will evaluate our function. F. So to make this perfectly explicit, I'm going to take those points and they're going to generate the widths of my intervals so that when I have the heights of my rectangles, the widths of my intervals are determined by the partition itself. So that one's determined by there, this one's determined by there, there. Ooh, this one's down below. Oops, I went too far. Oh, what did I just do? That's okay. Oh, there's an undo button. Yay! Okay. I almost started crying there for a second. Don't push the clear entire page button. Okay. 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 So that diagram kind of illustrates what we're going to do to define the integral. What we're going to do is we're going to take the widest interval here, and we're going to drive it to 0. We want the width of the widest interval to go to 0. I'll do this in green because I think it shows up really well. All right, our goal is to take the width of the partition. That's the width of the partition. I'm going to take that to 0 and watch the area of my rectangles. All right, and that's going to go to the integral. Okay, let's turn the page. I think I have enough for that page. All right, so definitions. A partition of an interval a, b of size n is a set of subintervals that make up the interval from a to b. The subintervals only overlap at their endpoints. And the set of sample points is a set C is a set of C sub i's, where C sub I is in x sub I minus 1 comma x sub I, which is an interval defined by my partition. So we haven't said where the partition is coming from. Maybe the partition comes from a piece of computational software, or maybe the partition is defined by the uniform partition that we were working with in section 5.1, where all the subintervals are the same width. It doesn't matter. The point is that a partition breaks my interval AB up into n pieces, and then inside of each of those pieces, I have a sample point. Okay, so the width of a subinterval is defined as x sub I minus x sub I minus 1. It's the difference between it's the difference between the boundaries. And the width of the partition is equal to the maximum among the set of delta x sub i's. So among all the widths, which one is the biggest? Among the widths of all subintervals, which one's the biggest? Yeah, that's the width. Okay, so these pieces, the width of the subinterval and the width of the partition and sample points are going to be used to define this thing in here, which is this Riemann sum. This is a generic Riemann sum. Let's look at its pieces. So we're focusing on this expression right here. It's a sum, which we learned about in 5.1. I've got my sample point inside here for the ith interval. I've got the width of the ith interval. And then f at c sub I then is the height of the ith rectangle. And I'm summing them up. So all I've really done right here is write down a generic way of approximating an area using rectangles. That's all it is. That's all a Riemann sum is. The special ones that we learned about last time, we call them R sub n or L sub n, and I encourage you to learn about M sub n. Those are the right, left, and midpoint methods. Those are just special cases of R of F comma P comma C, where they're making the P be the uniform partition, and C is always left, always right, or always in the middle. It's just special cases. So all of that lets us set up this definition that we're going to focus our attention on here, and then we'll talk about the language or the symbology in this symbol right here. Okay, so this is the definition of the integral of the definite integral, and we'll talk about the definition of the indefinite integral in section 5.3. So this is the definite integral. The definite integral. This is read as the integral from a to b of f of x dx. That's how you narrate it. It's defined as, so some people like putting a little dot there to indicate that it's defined as the limit, cool, limits from chapter 2 coming back at us, as the width of the partition goes to 0 of the Riemann sum for the function, the partition, and my sample points, the points that happen to live inside of each of my intervals. On the next line, right here, I have just me replacing R of FPC with R of FPC. It's literally just the sum of the width of a bunch of rectangles. Of the area, sorry. Oh my gosh. Area of rectangles. Defined by the partition and the particular scheme used to generate your sample points. It's just the sum of a bunch of areas, and you take the limit as the width of the partition goes to 0. Now, the reason that we're not taking the limit as the number of points of intervals goes to infinity is that there's lots of ways that can go wrong. And I would encourage you to watch the class discussion from April 28 if you want to learn more about that. I'm not going to repeat that discussion right now because I don't want to get lost in it. So what we did was we wrote down a limit, right? And just writing it down doesn't assert that it exists. So if this limit actually exists, right, and is a number, or maybe it's a formula for generating numbers, if the limit exists, we say f is integrable over ab. So if f is integrable, then this limit exists. And if this limit exists, then f is integrable. So an integrable function, I can do this to it. And this doesn't look computationally feasible. And I think I agree with that. I think I agree with that statement. And that's okay, because in section 5.4, we'll learn how to do this. In the sense that we'll learn how to not have to use the limit definition to find these values. Okay, so we're still focusing our attention on the definition, and then the methods that we're going to use to exactly evaluate more or less arbitrary integrals is coming up in the future. What I want to do before we move on is really focus on notation. Because there are a bunch of pieces to this thing, and I think it's important that you understand what we call these different pieces. Let's see here. I think the newest thing right now is probably this symbol right here. That's the integral symbol. It looks like an S, and in fact it is. That S right there is a big long German S and is short for the word sum. It's kind of like the sigma is a Greek S and is short for sum. So the alliteration meaning here is strong. Okay, so we have this big long German S. Okay, so that just says we're doing an integral. Now this A, that's the lower bound, and B is the upper bound. It's not strictly required that A is less than B, but we like it when A is less than B. We'll look later at what happens when A is not less than B. This f of x, that's what we call the integrand. That's the function that we're going to integrate. And then dx, that's the differential. Now, a lot of people struggle with why we need the differential. And in a sense, it's the width of the infinitely thin rectangle, the differential. Why do we have it? Well, it represents the width of a rectangle. It's the thing that turns like height times width into area, because if you just have height, then you're just summing up a bunch of heights and you have another height. We need area, okay? And it's an analog, this d right here, well, that's like delta x. So dx is like delta x, except in the limit, delta x, which is some finite value, turns into dx. And there are good historical reasons for differentiating between those two things. So a differential represents the width of a rectangle. It also tells us which variable we're integrating with respect to. And that might not seem particularly relevant in this class, even for the remainder of the semester. You might continue to question why we have that. But pay attention, those of you who are going to go on especially to Calc 3, because what if I have f of x, y, and z, and I want to integrate it? Well, which variable am I integrating with respect to? I can only do one at a time. So which one is it? We need something here to tell us which one we're going to do, because we're going to do multiple integrals later, and it tells us the order of integration. So the differential tells us the order of integration, and it's important because we want to execute it correctly. So that's why the differential is so important. So expect to be nitpicked that you get your differentials in place. Okay, let's turn the page. Okay, so we just defined the derivative in terms of a limit, right? Or not the derivative, the integral. The integral from a to b of f of x dx is equal to the limit as the width of the partition goes to 0 of r of f p c, which is this nice formal object. So when does it exist? Well, it's easy to say when it's guaranteed to, and then there's a bunch of cases when it can. And there is a whole body of mathematical theory on integrable functions, which is far too deep for us to go into right now. This math thing just goes as deep as you want it to. Okay, so if f is continuous, or it's continuous except at finitely many jump discontinuities, not essential, not infinite, but jump discontinuities, then f is integrable. So this guarantees the existence of the integral from a to b of f of x dx in cases that look like that. I've got that. That's a nice, because I've got these jumps, right? I've got these jumps, but there's only finitely many inside my interval from a to b, and so the area underneath this curve, we can compute it. On the other hand, questionable is what happens to something that looks like that. What's that area? And we're not going to answer that question in this class. You got to go into Calc 2. You'll learn about something that's called the p-test, in Calc 2. It's a great test. Okay, so we need to focus our attention on what does this integral thing even mean, right? Like, so I can write down this integral from a to b of f of x dx. What does it mean? We approximate it using a bunch of rectangles. Fine. It's the signed area of the graph of between the graph of f and the x-axis. It's the signed area. So if I have a function that looks like that, And my interval, I think I want to change its color. And my interval is red here. So that's my interval of interest. The area bounded between the graph and the x-axis is this entire area. And it's signed. That area counts as plus. This area counts as minus. It's signed. Anything below the x-axis, any area below the x-axis counts as negative. And that's because this stuff is all about net change. Area underneath the x-axis, like this area right here, that area is essentially net loss because the rate was negative. F of x represents a rate of change, and if that rate is negative, then it's decreasing. And so the area counts as negative. So if I take a function, say this one right here, and I integrate it between A and B, then the entire area is positive. And it's possible to have functions, of course, that live entirely below the x-axis. And then that area down here, bounded, that area right there is entirely negative. Because the function that is our integrand was entirely negative, and so it was decreasing the entire time. So we're thinking of f now as being a rate of change, and it's below the x-axis. And so whatever I'm integrating this to, whatever f is the rate of change of, was decreasing the whole time. Okay. Rather than dwell on that, let's go ahead and move forward and talk about some ways to evaluate definite integrals. And that's going to be by geometry because we're talking about areas. So until we get to the fundamental theorem of calculus, specifically part 1 in 5.4, we need to and build a bridge between the integral and d dx. We don't want to use the limit definition to compute integrals because it's challenging. So what we're going to do is we're going to turn to our friend geometry to learn how to integrate it first, just to build our skill in recognizing that the integral is an area. It's a net area, a signed area. Let's start with the simple functions. Let's let f of x equals k for some constant function. So k is a constant. And it doesn't matter whether it's 0 or negative or positive. Let's take an interval, shall we? From a to b. And let's consider a function. That's a constant function. We'll see if I can do better. There we go. That was better. So when I draw that area, what geometric form is this? What did I just draw? What shape? You've been studying this shape for a long time. That's right. I just drew a rectangle. The width of the rectangle is b minus a, and the height of the rectangle is k. So what's the area of that rectangle? K times b minus a. And it didn't matter if I drew that constant function above, it would have worked the same thing as below, right? So the height of that constant function is the thing that sets this thing right here. And if it's negative, then, well, this area counts as negative because the k would be negative. This thing right here is going to be positive. unless the thing is out of order, which it's possible. So that tells us then that for any constant function, f of x equals k, the integral from a to b of f of x dx is equal to k times b minus a. It's just the height times the width. Constant functions are trivial to integrate. All right. So definite integrals of constant functions correspond to rectangles. And we know how to deal with rectangles. We've known how to deal with those for quite some time. Let's level up a little bit and talk about linear functions. So what I'm going to do is I want to throw down a couple of plots of linear functions. One of them is an absolute value, and I wanted to bring absolute value up because there's some really interesting things that happen with it. And students are often uncomfortable with absolute values, and so it's good that I bring them up periodically. I also learned how to make two of the quadrants appear in my blank axes, so I just leveled up myself. I continue to learn. Let's draw these two functions, shall we? These two integrands. Let's put 3 minus x on the one on the left, right? Let's do that one. And then over here, let's do absolute value of 3 minus x. And let's do the 3 minus x one first. Okay, so its slope is -1, and its intercept is 3. 3, and its slope is -1. Alrighty. So so far, all I did was draw it, and when I take the absolute value of it, absolute value makes negative values positive. So it's going to take these negative values and it's going to flip them. So when I draw my absolute value function, it's still going to pass through 3 right here, and it's going to go down like this. But when it hits there, it's going to start going back up because it's always absolute value. Right? That's equal to 3 minus x if x is less than 3, and minus 3 minus x if x is bigger than 3. And we'll throw the equals onto one of those two things. Right? So all it does is take minus to do the flip. So that minus right there does the flip, boop, to put it up. Because taking minus a function flips it across the x-axis. Okay, so I have drawings of my two things, and you might already kind of see where I'm going with this when I start computing definite integral. So we're going to compute the integral from 0 to 5. From 0 to 5. Let's shade. I wish I got a chisel tip with the highlighter. That's okay. So my area, is that even legible? I don't think so. Let's do green. So my area here is this area. And my area on the right-hand side is this one. All right. So one conclusion I think we can immediately draw is that the integral from 0 to 5, the absolute value of 3 minus x dx, is bigger than 0. Because all the areas above the x-axis, and I think that over here it's like kind of ambiguous, except that this area here counts as plus, this one here counts as minus, but that one's bigger. So I think we can also conclude that the integral from 0 to 5 of 3 minus x dx is bigger than 0. Let's compute them exactly, shall we? Let's focus our attention on this one at first. So we're going to use geometry to do this because I don't have the symbolic tools available to me yet. If you've taken a class previously, you might be like, yeah, I know how to integrate, in which case, like, by all means, do it to check your work. But we're trying to drive home a lesson here. Okay, so I've got two 45, 45, 90 triangles here because the slope was -1. The base here was 3, the height was 3, so the area of this triangle right here is 1/2 base times height, which is equal to 9/2. And the area here is 1/2 times 2 times 2, 1/2 base times height, which is equal to 2. That means that the integral from 0 to 5 of 3 minus x dx is equal to 9/2 minus 2 equals 5/2. Right? We're just using geometry to answer these questions because the area, the definite integral, is the signed area under the curve. Let's do it for the absolute value. This one right here, the area is still 9/2. I already computed that. That area, I still have a 2 root 2 triangle, 45, 45, 90 triangle. Its area is still 2. The integral from 0 to 5 of the absolute value of 3 minus x dx is equal to 9/2 plus 2, because they're both above the x-axis, which is equal to 13/2. So linear functions correspond to triangles. In particular, right triangles. Because we're always cut by like a point like A or B, and we're always drawing vertical lines from those, whether we're going below or above. And so we always have a right triangle. So 1/2 base times height is totally your friend. Our book does derive one more formula here, and that's on page 301. I don't want to repeat that calculation right now, because what they do in order to do this is they take the limit as the partition width of the partition goes to 0 of r of f p c for a specific partition in C. They do it by formula. They invoke a particular sum of something squared at some point, and then do the limit. And I didn't feel like it was going to be particularly enlightening. And so instead what I did was I said, well, okay, let's take this formula here and focus on it, and maybe we'll find an opportunity to use it. All right, so the integral from 0 to b of x squared dx is b cubed over 3. This works if this is a 0. This is wrong if that's not a 0. That must be a 0. I should write that in red, shouldn't I? Or this is wrong. All right, let's turn the page. We're making good progress here, I think. Finally, we're getting to the really super useful part of this section of the book. In particular, so we're done with the definition of the integral. We talked about some geometric objects that you can use to evaluate some integrals. And so now we want to talk about, okay, I've got this new notation, the integral from a to b of f of x dx. How do I push the symbols around? Like, what do the symbols do for me? And this is where we have these theorems in the book that help us manipulate these expressions. And so I wanted to talk with you about these 4 points in this. So let's suppose that f and g are integrable, right? That is to say that the integral from a to b of f of x dx exists, right? It's a number. Or maybe it's a formula that generates a number. Let's not get hung up on things always be numbers. Maybe there's a parameter in it. That's fine. So does G. All right, so those both exist. Both those integrals exist. Then I conclude that the integral from a to b of f plus g dx exists. That is to say, I get a number or formula. The limit exists because the integral is defined in terms of a limit. What's cool is that I also know that the integral from a to b of c times f dx, that exists. I furthermore know two really excellent properties that really help me out in a lot of situations here. These are the linearity properties. The first one says that the integral of the sum is the sum of the integrals. So I can split, right? Boop, I can split my integral and I get two integrals with a plus in between them. That is so incredibly useful. I also know that the integral from a to b of c times f of x dx is equal to c times the integral from a to b of f of x dx. So that c comes out front. Boop, I get to pull it out front. These properties were similarly true for limits and were similarly true for derivatives. This is what's called the linearity of the integral. And we call it linearity because the definition of an operator being linear is that these properties happen, namely that bullet point, that bullet point. If I can split it according to pluses, and if I can pull constants out front, then the thing is linear. And this begets the whole world of linear algebra. I do hope some of you go on to take it. Linear algebra is some of the coolest theory in mathematics, and it is absolutely prevalent. Your phone does linear algebra all the time. Not theory, but algorithms from it. For example, let's use the linearity to compute this, shall we? So we're going to justify our steps. No problem. The first thing that I'm going to do is I'm going to rewrite this as the integral from 0 to 3 of 2x squared plus minus 3x plus minus 7 dx. All I'm doing there is explicitly showing you that I have pluses, so that when I go to this step right here, the integral from 0 to 3 of 2x squared dx plus the integral from 0 to 3 of minus 3x dx plus the integral from 0 to 3 of minus 7 dx. Yes, I have a dx in each of those three places. That's why I had parens here, because that dx is against all of those. In order to be dimensionally correct, that has to be true. Okay. So the next thing that I want to do is I want to pull out my constants. Maybe I'll do that in red here. So my constant 2 is going to come out front. My minus 3 is going to come out front. My minus 7 is going to come out front. Maybe I'll leave that minus 7 inside and just use the constant function rule on it. I think that's what I'll do. So 2 times the integral from 0 to 3 of x squared dx minus 3 times the integral from 0 to 3 of x dx plus the integral from 0 to 3 of minus 7 dx. Oh, you know what I think I forgot to give you was the formula for the area underneath a line. But I think it's going to be okay. I think we can work it out. Yeah, it's going to be fine. Okay. Yeah, it's going to be fine. All right. So this is equal to 2 times. Now I need to deal with x squared. The integral of x squared is from 0 to b is b cubed over 3. So to this one right here, I'm going to get 3 cubed over 3 because that was b, upper bound, minus 3 times, now I have a triangle that looks like that. So times 9/2 plus, ooh, I've got a rectangle, minus 21. And now I just kind of like do the steps. So this is equal to 18 minus 27/2 minus 21. 36/2 minus 27 halves, I don't know where to do a 6 there, minus 42/2 is equal to 9/2 minus 42/2 minus 33/2. Okay. Now, I guess I didn't write in my justifications. This step here to here was put in. Oh no, that was used linearity. We use linearity. And this is of plus, and this is pull out constants. And then going to the next line is use geometry. Yes, I know we didn't use geometry for that part of it. We used a formula that was derived by our book. That's the way our book is presenting this information. All right. So the linearity is so nice because it means that I can just deal with each of these three pieces separately. I don't have to deal with them all together. I can just deal with that part, and that part, and that part. And the annoying constants that are inside, I can just pull them out front of their respective integral symbols. All right, there are a few more properties that I think it's really important for me to communicate with you. I have one whiteboard video that I'd like to point out. It's called Properties of the Definite Integral, and I think you should watch it. The content overlaps significantly with what we're doing here, but it's a different format. Okay, so the first one that I want to do for you is additivity of adjacent intervals. So what if I have two adjacent intervals and a function like that? Well, I can treat this as two areas, or I can treat this as one area. If I treat it as two areas, it's going to tell me that the integral from a to b of f of x dx plus the integral from b to c of f of x dx those two areas separately. Well, if they abut directly against each other, then that's equal to the integral from a to c of f of x dx. So I can smoosh things together, or I can split them apart. So I know that the integral from 0 to 5 of f of x dx is equal to the integral from 0 to 2 of f of x dx plus the integral from 2 to 5 of f of x dx. So I can split or I can merge. Okay, comparison theorem says if f and b are both integral, and I know that f is less than g over my interval, well, then I've got a situation where I've got an interval from a to b, and I have a couple of functions. I know that, and it doesn't matter whether they're below the x-axis or not, just as long as f is less than g, right? On that interval, f is always less than g. It doesn't if there's a crossing over there, fine. We're focusing our attention inside of here. It doesn't matter what's happening out here, unless we're talking about that interval, in which case it does. Then the integral of from a to b of f of x dx is less than the integral from a to b of g of x dx. G is always higher. Area is always more. And this includes if things are negative. It's perfectly exactly the same below the x-axis. So I can take that and put it below the x-axis, and the statement's still true. This next one is really similar, this bounding property. I'm going to move this up so it's not bothering me. So if I have an interval from a to b, and I have a function, and then above it I have an m, well, then I happen to know that the integral from a to b of f of x dx is less than, well, I would write the integral from a to b of m dx, but that's just a constant. And so the integral is m times b minus a. So I've got a rectangle, and that's more than the area underneath this curve. Guaranteed. Guaranteed. The next one, reversing the limits of integration. This one's really cool. This one says that the integral from a to b of f of x dx is equal to minus the integral from b to a of f of x dx. Essentially, it's like what happens if you run the system in reverse? Well, then the whole thing flips. It also means that the integral from b to a of f of x dx is equal to the integral from a to b with a minus sign. It doesn't matter, you can flip it, right? So I can write, I know that the integral from minus 5 to 2 of sine of x dx is equal to minus the integral from 2 to minus 5 sine x dx. That's fine. It also lets me do things like the integral from minus 1 to 0 of x dx. And if I don't like those being out of, sorry, no, I wanted those in the other order. 0 to negative 1, so they're out of order. It's like, I want this one to be bigger. It's like, okay, well, you can have your cake and eat it too. All you have to do is pay a minus sign, and you can flip it. Let's flip it. Flip it good. Finally, one more property I think that's super important to pay attention to, the zero width interval property, says that if I've got a number line and my intervals from A to A, then there can't possibly be any change regardless of what's happening on my function, so long as this doesn't have like an infinite discontinuity there or something like that. Delta functions, blah, 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 pulses. Take a course in partial differential equations sometime. It's awesome. Okay, this says that the integral from A to A of f of x dx is equal to a big fat zero. A big tasty zero. An egg, maybe. I love eggs. Just imagine that zero is an egg frying on top of a frying pan in butter. Ooh, with coarse kosher sea salt. Okay, these properties are awesome, and we're going to use them in a couple of pages, and you need to be really familiar with these. So I assigned plenty of problems related to these. Just a couple more pages. We are getting close to done, so we're going to do a couple pages of examples. So let's evaluate using geometry these functions. All right. If we're going to use geometry, I think we better use a picture. Essentially, this integrand that we're looking at here is like minus absolute value of x plus 2. And so that's like absolute value of x, reflect over x-axis, shift up 2. You follow me? So I'm going to take absolute value of x, which looks like that. I'm going to flip it over the x-axis, and then I'm going to add 2 and shift it up 2, and my function looks like that. That function is 2 minus absolute value of x. And we are interested in the integral from minus 2 to 4 of 2 minus abs x dx minus 2, 4. So we've got some area. Let's fill it in, shall we? Got some area right here. We got some area right here. And we got some area right here. That one counts as positive. That one counts as positive. That one counts as positive. No. What am I saying? That one counts as negative. It's below the x-axis. It counts as negative. Come on, Sylviana. You can do it. You can do it. You can do it. We're going to use geometry to do this. The first thing I'm going to do is I'm going to note that those two are the same triangle, but one's above and one below. Does those cancel? Because they're the same size. And of opposite sign. So the only one I need to work on is that one, and it's a 2 by 2, but we're missing half of that square, right? And so this is equal to 1/2 base times height of that one triangle that's left over. It's 2. This is a super handy skill to have, my friends. Even as we learn the symbolics for doing this, it is such a good tool to have this geometry at your fingertips, because you can estimate, even if you have curves, you can still estimate about what things are going to be like, and then you can know, like, oh, I'm really wrong, or like I'm in the ballpark of right. And it's just a great way to check your work. So I think it's really important that you spend time learning how to do that. Sketch the signed area represented by the integral. Okay, I can do that. I prepared this just quadrants 1 and 4 because I'm nice. Let's rewrite this as the integral from 0 to 5 of x times 4 minus x dx. This is a downward parabola. Oop. And then I just want to know where its roots. It has roots at 2 and 4. Nope. Where did 2 come from? 0 and 4. 0 and 4. The peak is in the middle at 2. At 2, I would have 4 times 2 minus 4. So it's of height 4 there. So my parabola looks like this. And we're supposed to sketch the signed area. This area here is going to be plus, and that area there, if I can ever start writing the correct thing, it's going to be like that. And let's fill it in. It's going to be this area here and this area here, because we're going from 0 to 5. It's going to be positive because there's more above the x-axis than below. It didn't tell us to evaluate it, although we could. Maybe we should go ahead and do that right now. Let's go ahead and evaluate that right now. So let's use linearity. I don't know how to work on things that are factored yet, so we better not do that. So I'm going to write the integral from 0 to 5 of 4x minus x squared dx as the integral from 0 to 5 of 4x minus the integral from 0 to 5 of x squared. And if I want, I can pull that 4 out front, and I do want. Thank you very much. This x squared one right here, that's going to use that integral from 0 to b of x squared dx is b cubed over 3. So this is 5 cubed over 3. And then this is a triangle. This right here is a triangle of 5, 5, 25 over 2. 1/2 base times height. Minus 125 over 3. And 50 minus 125 over 3. There's no way I was going to do the common denominator. That sounded like it was going to suck. 150 over 3 minus 125 over 3 is 25 thirds. Huzzah! It was positive. I told you it was going to be positive because there's more above than below. Telling you, this geometry stuff is so good as ways to check your work as you go on with this. Okay, so this is going to be our last page for this. I really like this flavor of problem. These are really cool. So we're given 3 integrals, and we're going to use the properties to compute some other integrals. Or basically all that's changing on these ones is the bounds, right? So like I have the same integrand and the bounds are changing. So in terms of a number line, I know it from -2 to 1, and then from to 3, and then a 5. So from there to there is 6. From there to there is 2. Not the distance, but that's the integral equals. And then from 1 to 5, the integral equals 9. I hope my diagram makes sense at all. That's how I'm thinking about it. So now I want to compute the integral from -2 to 5 of f of x dx. Okay, so I need to compute that whole thing, and I happen to know it on these 3, from there to there, from there to there, and from there to there. So now I want to recognize, how can I make that out of those other pieces? Well, I can smoosh those together, and I get that entire thing. Okay, so I'm going to write that as the integral from -2 to 5 of f dx plus, nope, sorry. I wanted to go from -2 to 1, because I can go there to there and there to there, and that's the same as going that way. 1 plus the integral from 1 to 5 f dx. I'm going to suppress my of x's because it's not helpful to me right now. I know that integral from -1 to 2 was 2, and the integral from 1 to 5 was 9. So I know that the integral is 11. All right, so now I want to get the integral from 1 to 3. How can I construct the interval from 1 to 3 out of those other 3 pieces? Ooh, I think I got it. If I take that and I subtract that, then I'm left over with just that. Ah, yeah, so I'm going to write this as the integral from 1 to, come on, brain. I'm going to write that as the integral from -2 to 3 of f of x dx minus the integral from -2 to 1 of f of x dx. Yeah, because then I'm just left over with the piece I want, the 1 to 3. If I take this whole thing here and I wipe that part out, then I'm just left with that. Yeah, okay, great. Okay, so that's equal to 6 minus 2, 4. Oh, I like these. Alrighty, my friends. We have one left here. The integral from 5 to 3 of 2f of x plus 1 dx. Now, I don't know about you, but I am a little disturbed by the 5 and 3 being out of order, so we're going to pay the minus sign and flip. And now I think I want to split minus 3 to 5 2f plus the integral of the x from 3 to 5. That minus sign in paren is going to be with us the whole time, right? I had to be sure and split that across the whole thing as I split with that plus. Judicious use of parentheses, my friends. I think I want to deal with this integral from 3 to 5 of dx straight away. There's a 1 right here. The constant function is 1. So this is a rectangle of width 2 and height 1. And so its area is 2. Okay, so that's going to be nice because now I can just write this as minus something plus 2. And now I just need to deal with that integral. And so I need to figure out how we can construct the interval from 3 to 5. I need to get that interval from 3 to 5. I think I can do that by going the whole way and subtracting a little bit of that, and that leaves over what I want. Did we do this whole thing yet? From minus 2 to 5? Ah, we did. Yeah, it was 11. Okay. Let me be a bit more step by step. Integral of 3 to 5 f dx equals minus 2. And now we're going to split that thing. So that's going to be the integral from minus 2 to 5. All right. Integral from minus 2 to 5. Minus 2 to 5 the whole way. And I want just that piece left over. So now I need to subtract over the minus 2 to 3. Minus the integral from minus 2 to 3 f of x dx. Close that paren. Maybe I'll make those ones be blue so you know they correspond. I'm going to go ahead and distribute this minus sign across right here so I don't forget it. Yeah, okay, I think I'm still on point here. So now, and I previously computed that this value here was 11. Is that what we decided? Yeah, 11. And the integral from minus 2 to 3 of f of x dx, we were told that that's 6. Ooh, we got there. I like these problems because they really force you to deal with those properties of the definite integral that I think otherwise can be a little subtle, but they're really important. So I want to say thank you so much for engaging with this lecture today, and I will look forward to seeing you again in class soon. Thanks. Bye.